We're going to do a quick overview of types of functions when we're looking at a table to tell whether or not they're linear, quadratic, or exponential. We're going into our exponential unit, so it's good to be able to look at a table and be able to distinguish whether or not they're actually exponential or not. So the first thing we do, we're going to have 3 examples, and these are good for you to have. You should already have some of these copied down from previous in the year, but we're going to look first at the x's. So we're going to look at this first example here. So if I'm looking at 12 to 15, I say, how did I go from 12 to 15? Well, I added 3. And we always want to think about adding first, and I added 3. So we notice that as I go down, I did the same thing each one. So it's consistent. So now I'm going to look at my f of x, and remember this is the same thing as your y. So I'm going to say, how did I go from -2 to 5? Well, I added 7. 5 to 12, I added 7. 12 to 19, I added 7. This tells me the first time that I look on this f of x side, what I did was consistent by adding. If I do that the first time, this is called the first difference. And if it is consistent each time, that means I have a slope. So my slope is 7 over 3, change of y's over change of x's, and I know that this is linear. Now we've talked about how to make these equations. We're not going to go back into that right now, but we know by looking at this and notice that the first difference is consistent, that it's linear. All right, so let's look at our second example. 0 to 1, we know we had +1, 1 to 2, +1. We can see this side here is consistent with adding 1. So we're going to look at the second side. So if I think about going from 1 to 0, I subtract 1. 0 to 3, I add 3. 3 to 10, I add 7. And 10 to 21, I add 11. Well, that's not consistent. That's my first difference. So my first difference is not consistent, so I know immediately it's not linear. These, if I looked at them as slope, -1 over 1 would give me a slope of -1. A 3 over 1 would give me a slope of 3. So they don't have a consistent slope. So that tells me right there it's not linear. So now let's look again and go to the second difference. So we're going to go from here to here, and we're going to see, do we have something consistent? So -1 to 3, if I go from -1 to 3, I'm actually adding 4. 3 to 7, I'm adding 4. 7 to 11, I'm adding 4. This is our second difference. If our second difference is consistent by adding or subtracting the same value, this tells me it's quadratic. So this one is quadratic. We'll go more into detail about how to make those equations later. But this one is quadratic. So we know the first one was linear because it had consistency. Our x raised by the same amount. Our first difference was all consistent. Our second example, first side, the x's were all consistent, but our first difference was not. But when we looked at our second difference, the pattern, we've seen that it all raised by +4. Now let's look at the third example. So we have 0 to 1, this is +1, 1 to 2, +1, 2 to 3, +1. So that's consistent. So now let's go here. 1 to 3, if we think about adding, we get +2, 3 to 9, +6, 9 to 27. Automatically I know it's not going to be consistent here with what I'm getting. So if I go a second difference and look, I'm going to notice that's not going to work either. There's not going to be a second difference. So now if I don't see a first that's the same and I don't see a second that's the same, then I have to think, what did I do to multiply to get this to be the same? So let me back up and take away these little things here. So how did I go from 1 to 3? Well, I multiplied by 3. 3 to 9, I multiplied by 3. And 9 to 27, I multiplied by 3. So this tells me that I have a multiple of 3 to get to the next one. This is called a common ratio. Okay, a common ratio. And in this case, it's growing 3 times every time. So I started with at 1, and it grew times 3, times 3, times 3. So this tells me this is exponential. Okay, all right. So now let's go into identifying them in equations, exponential. So we're just looking for when we can tell in an equation if something is exponential or not. So if we look here at this first one, the first thing we need to look at, if we have an exponent that is a number other than 1, then we know immediately that it can't be exponential. Exponential is going to have an exponent of x. Okay, so we're going to go into the formula in a minute. So this is kind of asking you something before you know the formula. So if we just look at this first one, we see our exponent is 2. That immediately tells us this is quadratic. Okay, so this is quadratic. So when we think about quadratic, we think about our little graph will be something looking like that. And that's a parent function, but this is something similar with a little bit of change with that too. If we look and we see an exponent of a variable of x, then we know that this is exponential. Okay, so anytime we have a variable that is an x, it's exponential. Now, there's a couple other things that we have to make sure of. This variable can be negative or positive, but this base here can only be positive. Now, it can be a positive fraction, so it could be less than 1, or it can be a whole number, but it can't have a negative here. So this would not be exponential. Now, notice on this one, we have an exponent here, but we also have a 2. So this cannot be exponential because that 2 changes things. That is not exponential. This one, however, has a negative x. It is exponential. It just means that whatever number we put there, it just makes this grow down or decay. We're going to learn about that. So this is exponential. And then the last one is an example. We have x and we added something to it. This is exponential. So we can add or subtract something to our x and our exponent, but we can't multiply like we did here. Okay, so these are some examples to help you identify. And we know if we have something like y equals 2x, this would just be linear because our exponent here is just a 1. It's imaginary, but it's there as a 1. So now let's go into the formula for exponential functions. So we're going to talk about them as 2 separate ones, but you're going to see that once you understand how it's made, it's much easier to think about it as one formula and then just kind of what is the difference. So we're going to talk about it separately as growth and decay. So when we think about something growing, it's getting bigger. So if I give you $1 today and then it grows by a factor, by a common ratio, like in our example at the top, then we see that we've got $3 the next day, and then it grows again. We've got $9 the next day, which would be pretty awesome to have something growing that rapidly in our bank account. So this is a very detailed formula to kind of make you see the differences, and they shortcut this formula a lot to show you, and I'll show you an example of that. So for growth, we have f of x, remember f of x is just y, equals a times b raised to the x power. Now, an exponent's always going to have an x power. That exponent's always going to be x. Our a is the initial value. It's like the starting point. And that starting point we can find when we plug in 0 for x, okay? And then b is our growth factor, and it's a positive number. So when we're talking about growing, we're talking about something that is bigger than 1. Okay, so there's some rules that you have to remember. A has to be greater than 0 because if we start with something, we're not starting with nothing. We're starting with something, at least 1. And then B has to be greater than 1. So it could be 1.1, 1.2, it could be 5, it could be 1,000, whatever, but it's how something is growing. Okay, so it's not a negative number, it's a positive number, but it can be a fraction that is greater than 1. Okay, now for decay, we have the same formula. Initial, A is still initial. However, when we talk about the B in decay, when we're looking at something being decaying, we're looking at a positive fraction. So it's less than 1, but it's still greater than 0. Still not a negative number. We don't have negative numbers as our bases here. Now, x has to be any real number, so it can't be like irrational number, like the square root of -2 or something. It can't be imaginary. It's going to be a real number. It could be a negative number, -8, -8.2, 9,999, a million, but it's got to be a real number. Now remember that a factor, whether it's growing, because it's bigger than 1, or it's decaying, it's less than 1 but greater than 0, is the same thing as a common ratio. It's what we're multiplying by. Okay, so it's really important to kind of understand how these formulas work, and it'll help you more when you see them. So we're going to kind of go with some really basics here. So we're going to talk about how a basic problem would look and how you would graph it and how it would look on a graph. So we're going to use just the basic formula. We have a b, or a growth, and I'm going to just say ours is going to be f of x is equal to 2 to the x power. Okay. So if we needed to take this and find exactly what this would look like on a graph, we could pick some numbers. And you want to pick easy numbers. So remember, we like to pick 5 at least. We want to pick some negative and some positive. So I'm going to just pick our normal 5 that we do, the -2, -1, 0, 1, and 2. Okay? And I'm going to plug this in. So if I think about what I have here, my formula, my 2 to the x, if I plug in -2 into my x, because that's what that means, my x is -2, and I plug it into right here. So this would be 2 to the -2. This is not a negative answer. Remember, we did exponent. So anytime we have a number raised to a negative exponent, that's the same thing as having this number be at the bottom as a positive exponent. So this is the same thing as 1 over 2 to the 2, which is the same thing as 1 over 4. So that's 1/4. Same thing we do here. 2 to the -1 is the same thing as 1 over 2 to the 1, which is 1/2. Now, if we put in a 0, it's 2 raised to 0. Remember, our exponent rules, anything raised to 0 is actually 1. And then 2 raised to the 1 is 2, and 2 raised to 2 is 4. So now we have some points that we can plot on a graph. So I'm going to start at this 0, because we know if this is our f of x line, our y line, and our x line here. So if we're here at 0, I'm going up to 1. So that's where it's intersecting. And that's going to be true for any number that we have. The only thing that this 2 changes is how quickly it grows, how curved it is. And we'll talk about that more. So now that I look here, I want to say, okay, well, if I have a 1, so here's 1, I'm going to have this at 2, 1, 2. If I have a 2, I'm going to have it at 4. So this is 1, 2, 3, 4. And it will continue that path. So now let's do our negative numbers. A -1, we're going to have a 1/2. So I'm going to eyeball it. A -2, we're going to have a 1/4. So I'm going to eyeball that. Now, if you'll notice, this does a curve, and it will go forever and ever. Now, there's some vocabulary we have to know. So if we continue on with negative numbers in our x's, let's say we did -3, -4, notice that these got us fractions. So this would be like 2 to the -3, which we know is 1 over 2 to the +3, which is the same thing as 1/8. And 2 to the -4 is 1 over 2 to the 4th, which is 1/16. We can continue on and on and on, and it kind of gets closer and closer and closer and closer to this 0, this line here, but it will never cross it, okay, with exponential functions in this format. So this is called, this little line that it gets to is called an asymptote, and they usually do it with a little dotted line. And to show it, this is called an asymptote. So you need to make sure you write this down. And the asymptote for functions, exponential functions like this, is y equals 0. It's going to approach that line of y equals 0. Remember, y equals 0 is right here. But it's never, ever going to cross it. It's not going to go down here, okay? So this is something we're talking about growing. So we started here, and it's growing. As that got bigger, it's growing. Now let's talk about domains and ranges. So when we're talking about domains, domains are your x's, or your x values. So think about any number we could put up here for x. We could put any negative number. It's just going to give us a smaller and smaller and smaller fraction, but never going to cross 0. So it's going to continue this way forever and ever. If we put a big, huge number in there, we're just going to get further and further way up there, but it's going to continue along that path. So when we think about domains, we think about what can they go to. So domains are your x's. So in this case, we're having a negative, so it's going to go, because it's going this way, that's negative numbers, and remember domains are your x's. So we think about our x's right here. What's happening? These are the negative numbers, and these go positive. So we have negative infinity, so our numbers go negative infinity, and forever and ever, if we put in something here and it goes up, it'll somewhere attach up there way at the top, but that's a positive infinity. So our domains are positive, negative infinity to positive infinity, so they go on forever. All right, so here's an example of decay. So I use my function f of x is equal to 1/2 raised to the x. So notice that my half is smaller than 1. It's still positive, and I still have an exponent of x. So I know it's exponential. So I did a quick little graph, a little table to come up with my points, and I went ahead and graphed. And notice that when we have decay, I started over here on the left side, and it went down. My asymptote is still y equals 0. It approaches this x-axis, but it never crosses it. So that's still the same thing as when growth. But notice that this smaller number, it goes gradually down, and it's going to the right and moving off. If we have growth, we may start somewhere here, and then depending on what it is, it can grow. It can grow here, and it can still come down, and it's going to have an asymptote that is still y equals 0. The size of the base depends on how quickly it rises. So let's say this is 2x. 2 to the x, 2 to the x. But if we have something that's, say, 8 to the x, it's going to rise much faster. So when we think about putting in something that has a higher growth rate, we're going to see something that raises at a much faster rate. And you can use Desmos to kind of see the differences in these as well, to help you see how quickly. So if I have something that is to the 8th, it might take off a little faster and go a little steeper. So the higher the base, it takes off to the right much faster, and it's a little bit closer as we go. It might be a little bit closer to the asymptote, but it still never crosses. All right, so we're going to look at a table, and we're going to be able to write an equation from a table. And some of these get pretty tough, but we're going to talk about the basic things you have to know. So I went back to our formula. It's a little bit more distinct. Y equals AB to the x. Remember, y is the same thing as f of x. You will see it interchangeable, so just get used to kind of knowing that that's the same. So the first thing we got to do is be able to find our A and find our B. So remember, our A is our initial, and our initial is always when x is 0. So if we look at our table and we look and find where is x 0, that will help us determine what A is, our initial value. So when x is 0, where did it hit the y-axis? Where did it cross? So we can see that that's 2. Okay. Then we have to find our common ratio. And remember, our common ratio is how do we go from 2/3 to 2, 2 to 6, 6 to 18, 18 to 54. What number do we use to multiply? Common ratio, or factor, growth factor, or decay factor, depending if it's growing or decaying. Well, we can see that this is, as the numbers get bigger, -1, 0, 1, 2, 3, these numbers, 2/3 to 2 to 6, they're getting bigger. So we know this is growing. So I would not start with 2/3 to 2 and say, what did I do to multiply? Sometimes that's a little tougher. So look at 2 to 6. Well, what did I do to go from 2 to 6? 2 times what is 6? Well, that's 3. Well, 6 times 3 is 18. So I know that 3 is my growth factor. So that's my value for B, is 3. So now let's put it into the form. F of x, or y, is equal to 2 times 3 to the x power. Now, We can simplify this down a little bit and check to see if we're actually right by plugging in what we found as 0, 2. So that says when x is 0, so when this value is 0, so I'll use a different color, so 2 times 3, so when this is 0, our f of x should be 2. So let's see if that's true. Well, 3 to the 0 power is 1. 1 times 2 is 2, so 2 equals 2. So that's true. So I know that this is the correct equation. So we've already talked briefly about how to graph, but if you're given one that where you have the initial, so this initial is 1, and our growth factor is 2, because that's what's our base of our exponent x, first thing we're going to do is make a table. We're going to pick 5 numbers. So x and f of x, and we're going to pick 5 numbers. And you can pick any 5 numbers you want. Pick easy numbers. I'm going to pick our basic ones just for this example, but when you're dealing with some other numbers, you might want to pick numbers that are easier, depending. So I'm putting this into this problem. So I'm thinking about what I'm putting in. This negative 2 is going to go in for my x. So it's like saying 1 times 2 to the negative 2. So I know that 2 to the negative 2 is really 1 over 2 to the 2, which is 1/4, times 1 just still gives me 1/4. Okay, so when my value for x is plugged in here, my output, or my f of x, my y, is 1/4. And I do the same thing here. 1 times 2 to the negative 1 equals 1 over 2 to the 1, which gives me 1/2 times 1, which is 1/2. If I plug in 0, I'm getting 1 times 2 to the 0. Well, 2 to the 0 is 1. 1 times 1 is 1. If I plug in 2 to the 1, 2 to the 1 is 2. 2 times 1 is 2. And then if I plug in 2 to my problem for my x, 2 to the 2 is 4. 4 times 1 is 4. Then I would make my graph, and I would plot my points. So remember, this is our y, or f of x, and this is our x. I like to always start with my initial wherever it is. So when x is 0, where is it? It's at 1. And then I'm going to move up and look at the other pieces. So a negative 1, or 1, we'll do 1 first. 1 will be at 2. 2 will be at 4. And then my negative numbers, negative 1 will be at 1/2. And negative 2 will be at 1/4. So this shows what my shape would look like. All right, so I'm going to give you another one to try, and you can pause the video and try it and then see if you're right. So the other one is going to be f of x equals 2 times 3 to the x. All right, so this one's been done. Now, when I got up to 2, I guess 18, I didn't make my graph big enough. But notice we have some fractions that are repeating here, so you kind of have to eyeball them. So these can get a little harder to graph individually when you're having to deal with repeating numbers like 2/3, things like that. But that's why Desmos is very helpful to help you see. Now notice the difference in this graph when we have an initial value that is different than just 1. We grew much faster, so it rose much quicker. It's more steep. This is still growth because we had a growth factor of 3. But our initial being 2 raised where we hit at 2 instead of in our previous ones where it hit at just 1. We had an initial of 1. So that has some factors into where it hits the y-axis. Now do not confuse this. A lot of people will try to do this. They'll say, well, let me make this simpler and I'll multiply 2 times 3 and get 6 to the x power. That is not the same thing. Do not do that. This is our formula. It's going to look very different. If you graph it as 6 to the x power, you're actually going to get something that hits here, and it's going to raise, and they will eventually hit each other. They'll cross each other, but they are not the same function. So do not simplify that. Remember, exponent rules or PEMDAS rules won't allow us to do that. All right, the last thing we're going to talk about with functions today, with exponential functions, is how to evaluate them. So like before, when I gave you a linear equation and I told you what something the input was, you had to find the output. So f of x is equal to 3x. That's our formula, that's our rule. If we look at this, we can say, oh, this is growth of 3. I don't know what the initial is, so I'm assuming it's 1 because there's nothing there. Because it can't be 0, it has to be greater than 1. So 1 or greater. And we say, okay, well, I can put in our value of 2 into our x. So to evaluate this is f of, when I put in 2, what will it be? So 3, put in 2. I know that f, when I input 2, my output would be 3 to the second power, which is 9. So when we think about this on a graph, when my input is 2, my output for this function, 3 to the x, is 9. That's what I'm doing. All right, so let's look at example B. So my input, I'm telling you, is going to be 2. We can see that this is growth, but we have a negative in front of our exponent of x. It's still exponential, but that's going to change how we evaluate a little bit. So we say f of 2 is equal to 4. That negative is part of, we're plugging in the x, so we have negative 2, which is the same thing as 1 over 4 to the positive 2, which is 1/16. So if we think about this in terms of a table, when we input, our input is our x, we put in 2, we get out, for this function, 4 to the negative x, we get out 1/16. All right, let's look at this C. So f of negative 3, negative 3 is our x. So we're going to plug that into where we see our x, so we get negative 3. So this is the same thing as saying, think about what's happening. We can apply this for our exponent rules to each one. So 1 to the negative 3 over 2 to the negative 3. And then we want to make them happy. So this would be the same thing as turning them upside down. So we can think about it as 2 to the third and 1 to the third. This gives us 2 times 2 times 2 is 8. And 1 to the third is 1. So this is the same thing as 8. Okay. You could have also seen this if this was a negative first. You could automatically flip it upside down, and this becomes then positive. You could do it that way as well. All right, and our last one, we have a couple different little pieces. We have a growth raised to negative x plus another growth raised to the x. So we're saying when f is 2, what is our output? Okay, when our input is 2, we have 1/4. We have a negative part of our problem, and we'll put in our 2. And then we have plus 3 to the 2. Now, let's go ahead and simplify that. Because this is a negative 2, we can go ahead and flip this upside down, and this becomes a positive 2. We can also work it out each individual piece like I showed you before, plus 3 to the 2. Now, let's simplify. Well, 4 over 1 is still just 4. 4 to the second power, 4 times 4 is 16. Okay, so that's simplified. And 3 to the second power is 9. Add those together, and we get 25. So in this rule here, when our input is 2, our output would be 25 when we're doing this rule. 1/4 to the negative x plus 3x.